In this video, we're going to review some of the foundational concepts that you should have learned in your first circuits class. So I want to start with voltage and current. And voltage is defined as the amount of energy required to move charge. Okay, so it's basically the separation of charges and how much energy is required to make that happen. So for instance, if it takes us 2 joules of energy to move 1 coulomb of charge, that would be 2 volts. And if it takes 4.8 joules of energy to move 1 coulomb of charge, that is 4.8 volts. And remember, a coulomb is just our unit of charge, which specifically is 6.242 times 10 to the 18 electrons. We don't talk about charge in terms of electrons because the numbers would be very large. So we use coulombs as our primary unit of charge. Now, potential energy is associated with a body and is defined by its position. So a lot of times we actually use the term potential when we're talking about voltage. And you'll hear me say potential at this point and so on, because those words are used for voltage all the time. Now let's talk about current. So if voltage is energy that we put into the system in order to move those electrons, current is the actual flow rate of the electrons in our circuit. So if you would imagine this copper wire, if we were to dissect that wire and put this plate perpendicular to it and count those electrons as they come through this area, that flow rate happens to be the current, which we define as coulombs per second. So 1 ampere, or 1 amp, is equal to 1 coulomb for every second. So current is describing the flow rate of those electrons. So basically, if this is your battery, let's say this is a 9-volt battery here, and you have your positive terminal here and your negative terminal here. What that means is you have accumulation of positive charges on the positive terminal and negative charges on the negative terminal. When we connect those together via this wire, we get this current flow. The electrons are trying to recombine on the other end to establish an equilibrium there, and that's why we get that flow that you see of electrons. So let's talk about current again for a moment. Here you see a wire connected to the battery, and then we have what we call a load on the circuit, which is in this case a lamp. And we need to talk about which direction that current is flowing. Does it go from the negative terminal, as you see here, back to the positive? Or does it leave the positive terminal and go back to the negative? Well, there are 2 different currents that we're talking about here. One is called electron current or electron flow. That is where we decide that the current is flowing from the negative back to the positive. However, in this class and in many others in engineering, we talk about conventional flow, and we actually assume instead that the current is flowing from the positive back to the negative. So in this class, we will be focusing on that conventional flow, where current flows from positive to negative. Okay, so voltage is the applied force or pressure that sets the system in motion, and the current is the reaction to that pressure. So we talked about one other property in circuits 1. We talked about resistance, and resistance is actually the controlling factor of that current. So we're putting this voltage in the system to get the current started, and the current flow will depend upon that voltage and also the resistance of our circuit. So let's talk about resistance. It opposes the flow of those electrons basically because it creates these collisions and friction between those electrons along that path. and converts that energy into heat and raises the temperature of the component and the surrounding wire or air. And so what we're seeing is that the higher the resistance, the more it will slow down the flow rate of those electrons, which is, of course, Ohm's law relationship. And I'm going to show you the Ohm's law wheel again, where everything on this portion of our wheel is how you could calculate voltage, or how you could calculate current or resistance, and of course power. But really you only need Ohm's law, which again tells us that V is equal to current times resistance, or current is equal to voltage divided by resistance, or resistance is equal to voltage divided by current. And you need your power equation that tells you that power is equal to voltage times current. From these, well, basically these two relationships, we get all of these other equations. So if you're looking for power in a circuit, you could use it finding V squared over R, I squared times R, or V times I, and so on. So this is how you might use the Ohm's law wheel. It's just all of the iterations of the Ohm's law equation, V equals IR, and P equals V times I. So between those two equations, you can find all of the others. So you need to be familiar with how to calculate Ohm's law. Hopefully this is second nature to you now, but basically the current flowing through the resistor you see on the left, that would have to be whatever the voltage drop across the resistor is divided by the resistor value. So we've got 16 volts there divided by 2 kilo ohms of resistance. So we must have 8 milliamps of current through that resistor. Now for the second example, we know the current going through the resistor is this 1.5 amps, and we've got a resistance of 80 ohms. So if we're looking for the voltage, that's going to be I times R. And remember, for voltage, we tend to use E to denote a voltage source and V to denote a voltage drop in your circuit, although they are also used interchangeably as well. So we have 1.5 amperes times our 80 ohms, which means we must have about 120 volts drop across that resistor, according to Ohm's law. And your power equation. Let's look at our power equation. Let's say we are applying 120 volts to our motor here, and it's drawing 5 amperes of current. So our power equation, V times I, tells us that we must be drawing 120 times 5, or 600 watts of power. So make sure you're familiar with those equations. Okay, let's look at our series circuit here, and I'm going to just work with, let's see, let's work with this circuit. The other one, you can find both of these in your book, but let's work with the second circuit here. So in series, remember our total resistance is just the sum of the series resistors. So I'm going to find that first, because finding the total resistance will help me find the source current coming from that source. So RT for, remember, for this circuit, would be the 7 ohms plus 4 plus 7 plus 7, or 25 ohms. The reason I do that is because when you're looking at the voltage source, that voltage source sees a certain amount of resistance out there. It doesn't necessarily see 4 series resistors, it just sees 25 ohms of total resistance. So it's important that we know what resistance is seen here at the terminals of our voltage source, because that will allow us to use Ohm's law to find our source current. So E in this case is our 50 volt source, we have 25 ohms of resistance. So we must have 2 amps of current coming from the source. Okay, so I'm going to draw this in. Remember, we said our conventional current goes from the positive back to the negative. So if we have 2 amps of current here, since R4 is in series with our source, we're going to have that same 2 amps through here. And since R3 is in series with R4, we have that same 2 amps through here. Basically, there's nowhere else for the current to go. So we're going to continue to see that 2 amps all the way through our entire circuit and through every resistor. And that's going to help us when we go to calculate our voltage drops across those resistors, because we know the current through each one. So the voltage drop, I'm going to start with R1 here, would be R1 times I1 for any circuit. Remember that subscript notation is referring to the resistor we're talking about. So the voltage drop across resistor 1 is equal to the value of resistor 1 times the current through resistor 1. So we know that we've got a 7 ohm resistor here, and we have 2 amps of current. So that's 14 volts. Now notice that R3 and R4 are also 7 ohms and also have 2 amps through each. So that 14 volts, we also see a 14 volt drop across R3 and across R4. So for V2, that would be the voltage drop across R2, which is R2 times the current through R2. We have 4 ohms of resistance here and still 2 amps through there because this is a series circuit. So we've got 8 volts of voltage drop there. Okay, so what does that mean? Let me get rid of some of this. That means that first of all, if our current is in this direction, that means that all our voltage drops are going to be in this direction. So if V1 is 14 volts, and V2 was 8 volts, and our V3 is 14 and 14. So there are our voltage drops. And remember, Kirchhoff's voltage law says that the voltage supplied by the system should equal the sum of the voltage drops. You'll have to pay close attention to the direction when we get to having more sources, but this means that our 50 should equal to 14 plus 8 plus 14 plus 14. And the 3 14s is 42 plus 8. It does equal 50. Okay, so that works out. All right, let's look at another series circuit here. And notice here we're given the current, we're given RT, we're given R2 and R3. What we're looking for is R1 and the total voltage supplied. Okay, so a couple things here. One is to notice that we have the current through R3 and we know R3. So that can actually give us the voltage drop across R3. However, also need to recognize that I3 is not only the current through R3, it's actually the current through R2, through R1, and it's the current that came from the source. So I sub S is 6 milliamps. Now how does that help us? Well, if we know RT and we know the source current, then we should be able to use Ohm's law to calculate our total voltage supplied. So I sub S times RT, we have 6 milliamps times our 12 kilo ohms. So we must have 72 volts there. Oops. All right. Now, if we're looking for R1, we also know that R1, R2, and R3 are in series with each other. So R1 should be RT minus R2 minus R3, since we would just sum them to find RT. So that means we have 12 kiloohms minus 4K minus 6K. That means that R1 must be 2 kiloohms. Now, if you want to check what we've done here, what I would do is go ahead and find V1, V2, and V3 and see if they add up to that 72, just as another check. So for V1, we have 6 milliamps through a 2 k ohm resistor. So we've got 12 volts there. V2, we've got the same 6 milliamps through a 4 k ohm resistor, so that must be 24 volts. And V3, 6 milliamps times 6 kiloohms, or 36 volts. So if we were to add these up, we would indeed find that we have 72 volts of voltage dropped across R1, 2, and 3, which means that we're probably correct in our calculations. Okay, so a couple other quick points to make. Voltage sources in series can be summed. So in the first example here, you notice that they're all in the same direction. So we're going from minus to plus, then minus to plus, then minus to plus. So they're all oriented in the same direction, which means they add. So we've got 2 plus 6 plus 8, or 18 volts. In the second example, notice that we have minus to plus for the 4, so I would say that's a plus 4. Then plus to minus for the 3 going in that upward direction, so that's in the opposite direction, so I'm going to call that a minus. And then plus to minus 9, so I'm going to subtract that one as well. And when we add those together, we actually get a minus 8 volts. Now, when we're talking about voltage, the plus and the minus really only tells us about the direction. So what we're saying is the overall voltage is going to be the same shape as this and this voltage source. So when it was drawn over here, they drew it with the positive terminal down and the negative terminal up and called it 8 volts. So that's not a negative 8 volts, we're just saying that's the direction that we set in the beginning. So let's practice a little bit with Kirchhoff's voltage law as well while we're here. Remember, the voltage law tells us that the sum of voltage rises minus the sum of the voltage drops around a closed loop has to equal 0. So I want you to practice writing these equations. I like to start down here in the bottom left and go in this clockwise direction when I write my equations. And when I go from minus to plus, I add that. And when I go from plus to minus, I subtract that. So let's write an equation for this first circuit. Starting here and then going this way, I go from minus to plus, so I'm going to add that 60 volts. Continuing along, plus to minus, I'm going to subtract the 40. Continuing on, this is the unknown voltage, so we don't really know if it should be plus or minus. So we have assumed that we're going from plus to minus. So I'm going to assume that I subtracted, and we'll let the answer tell us in a minute if we were right or not. And then continuing on, minus to plus, I'm going to add the 30. When you get back to where you started, you set the whole thing equal to 0 and then solve for any unknowns. So my Vx, I'm going to move to the right-hand side so that it becomes positive. And then I'm left with 60 minus 40, which is 20, plus 30. So that must be 50 volts. in order for Kirchhoff's voltage law to be true, that would have to be 50 volts. Now, if this came back as a negative number, then my direction that I chose would be wrong. But since it's positive, it actually means that we had the direction right in the beginning. Okay, the equation for the second triangle here, triangle circuit, I'm going to do a -6 minus 14. Again, I'm going to assume a plus to minus on that V sub x, minus V sub x, and then plus 2 for the 2 volts to get back to where I'm started, equals 0. If I move the Vx to the other side, I have a -20 plus 2, or a -18 volts. What that means is that I have chosen the wrong direction. The direction actually should have been minus to plus 18 volts. Okay, so the negative is just direction. It's not really a negative 18 volts so much as it is direction with respect to something else. And voltage division. Time to talk about voltage division. Now, for your circuit, you can go ahead and analyze this just as we did the others, where you would find the total current and then multiply that current by each of the resistances to find the voltage. However, a voltage divider are series resistors. Okay, so I'm going to make a note of that. Series resistors are a voltage divider. Okay, you're going to need that going forward in other classes as well. So let's look at our circuit over here and discuss what we mean by a voltage divider. So in series, or in your voltage divider circuit, we say that the voltage drop across a resistor or an area of the circuit to the total voltage supplied to the whole circuit is the same ratio as that resistance to the total resistance of the whole divider circuit. And another way you might have seen this written is V1 equals R1 over RT times V1. So if we want to find, let's say, V1 right here, V1 equals that 2K ohm resistor over the RT. Well, RT would be the sum of 2 plus 5 plus 8, or 15 kiloohms, times, oh, that should be VT there. Sorry about that. When I solved for V1, that should have been VT. So 45 volts. So basically 2/15 of the 45 volts should be the drop V1. And that should be about 6 volts there. Okay, so 6 volts here. V2 would be 5K over 15K, or about a third of the 45 volts, which should be 15 volts. And then V3 would be 8K over the 15K times 45, which should be whatever voltage is remaining. It looks like 24 volts there. Now in this particular problem, I'm going to write this over here, 6 volts, 15 volts, 24 volts. And then I'm going to erase this because we're also looking for this V prime, which appears to be the voltage across not only the 2K, but across the 5K as well. So this whole portion of the circuit is where we're looking for the voltage drop. So for V prime, that would be the resistance across that whole area divided by the resistance of the whole circuit times, again, the 45 volts. And we should get there 21 volts. And notice that is the sum of our 6 plus 15. We will practice a lot more with the voltage divider rule this semester, so please go over that some more. Now for parallel circuits. In series circuits, we saw that the current was the same through our series elements of our circuit. Well, for parallel elements, we actually have the same voltage across the elements. So, for instance, if we're looking at our first circuit here, we know that V1 is equal to V2 is equal to the voltage source of 27 volts. So if we're looking for the current through R1, that's going to be V1 over R1. And we know that there are 27 volts drop across here and across here, because this point up here is at the same voltage level as here. There's nothing to change that voltage level from there to there. And we know that the voltage level at ground is the same voltage level here and here, because again, there's nothing to change that. So the same 27 volts from the source would have to be the voltage across each of our resistors. So back to our I1, we see that would have to be 3 amperes. I2, same 27 volts. We have 1.5 amperes there. Oops, that's 3. And that's 1.5. And Kirchhoff's current law tells us that the current coming into a node has to equal the current leaving the node. So the source current in this case would have to be 3 plus 1.5, or 4.5 amperes. Now what I didn't do is I didn't start with RT this time. We could have done that. And remember, when we have resistors that are in parallel, the equation we use to solve for that resistance is 1 over 9 plus 1 over 18. So the total resistance would be 6 ohms, and I sub S would then be my 27 volt source divided by that 6 ohms, or 4.5 amps, which we found right there. And that's great. If you have only 2 branches in your parallel circuit, then you could also find RT by doing what we call product over the sums, where you take your 9 times 18 over 9 plus 18, and you should get the same thing that we got up here. However, this equation always works. Okay, so feel free to use that equation. Now let's talk again about Kirchhoff's current law. Kirchhoff's current law says that the sum of the currents entering a node is equal to the sum of the currents leaving in the node, right? Current that comes in has to go out somewhere. So if A is our node right here, as we're showing, A is the node, what do we have? We've got 8 amps leaving, 10 amps leaving, and 2 amps leaving. And then I sub S is the only thing that's coming in. So I sub S must equal 8 plus 10 plus 2, or 20 milliamps. Now we could find out a few more things from our problem here. So let's say, let me go ahead and write down that 8 is 20 milliamps. Okay, notice that right here, we know two things. We know the current going through that resistor is 8 milliamps, and we know that R1 is 2K. So if we want to find the voltage, we would just take our 8 milliamps and multiply by the 2K, and that means we must have 16 volts there. Now, what else do we know? So if that is 16 volts, notice that this is in parallel with the source. So the source must be 16 volts. It's in parallel with R2, so we must have 16 volts there, and it's in parallel with R3, so we still have the 16 volts there. What can we find from here? Well, what would R3 have to be? It would be 16 divided by 2 milliamps, or 8K ohms. What would R2 be? 16 volts divided by 10 milliamps, or 1.6K ohms. And what would RT be? RT would equal E over I sub S, right? So we've got 16 volts over 20 milliamps. Which should be about 800 ohms. Again, there are always ways of checking your answers when you're working with in circuits. So what I would do is take our 2K, 1.6K, and our 8K and calculate RT. So RT would be 1 over 2K plus 1 over 1.6K plus 1 over 8K. And that should give you 800 ohms as well. So that would be a good check to do. All right. And the current divider rule. Now the current divider rule is the opposite of what you learned for the voltage divider rule. The current divider rule tells us that the current through R1 to the total current coming into the current divider is equal to the ratio of the total resistance to the resistor value, or I1 is equal to RT over R1 over times IT. So what you need to know are parallel resistors are what we call a current divider. They divide the current, just like series resistors divide the voltage. Okay, so in this case, if I want to find I1, first of all, I'm going to need to know RT, 1 over 1K plus 1 over 10K plus 1 over 22K, means that my RT should be about 873 ohms. So I1 should be RT over R1 times IT, where RT is 873 over 1 kilo ohm times 12 milliamps, and that gives us about 10.5 milliamps. I2 would also be 873, but this time over 10K. And that would be about 1.05 milliamps. And then I3, again, same RT over 22K, which should be about half of an milliamp. Let's get the right units here. Now, if we added this up, 10.48 plus 1.05 plus 0.48, we should get very close to the 12 milliamps that we started with. So that's the current divider rule. Okay, and this is all from chapter 6 if you want to review a little bit more. We talked about open and short circuits in chapter 6. Basically, an open circuit happens when you lose contact in the circuit where you should have it. For instance, a fuse might open up, or one of the contacts in the circuit opens up. Maybe a light bulb that's wired in series opens up. These are examples of open circuits. And remember, in an open circuit, there is no current, but there can be voltage, okay? Now, when we're talking about short circuits, the opposite is true. Short circuits happen when there's a path for current that is not intended in the circuit, and it can circumvent or go around the portion of the circuit where we want the current to go. So in this case, you see that a wire from the positive terminal that should stay over here has drifted over to the negative terminal, and that's a bad situation. Or here we have a twisted pair of wire and the insulation has rubbed off, or it's very tight, and that has then connected the two wires in a way that we don't want. Wire that's too tight might result also in a short circuit. Okay. So basically a short circuit is very low resistance where you would have no voltage across the short circuit, but you can have current. Okay, so make sure you remember those two things. So basically here in the first circuit, what we're seeing is that if all goes well in our circuit, we have 10 volts across 2 ohms of resistance. So we should have about 5 amps through here. And we have a 10 amp fuse, meaning as long as our current stays under 10 amps, we're fine. However, let's imagine that somehow we get this short circuit situation in our circuit and our current no longer has to go through our resistor. We say that our resistor is shorted out because current now has a path to take around the resistor to get to where it's going. So what happens here is now we have nothing to limit the current, and it gets very, very high in the circuit and gets the current goes above the 10 amps, and then the fuse opens. So once that happens, we now have an open circuit, and we go down to I equals 0 because we don't allow current to flow anymore. We want this fuse in place because if we allow that current to grow unbounded and it's connected to other things in our circuit, we're going to damage something or maybe start a fire, and we don't want that. So that's where we need one of these overcurrent devices in our circuit. So review the material on open and short circuits, and anything in this video, go back to chapters 5 and 6 and try to brush up on series and parallel. And in the next video, we'll talk about series parallel combination circuits.